Hello everyone. I'm Shuji Wan from Tianjin Normal University. Today, I'll present our team's CVPR 2026 work, ADA-S-Former Adaptive Serialized Transformers for Monocular Semantic Scene Completion from Indoor Environments. My collaborators include Xinran Wu and Ziping Zhao from our university, Song Wang from Zhejiang University, and Lingdong Kong from the National University of Singapore. Indoor monocular semantic scene completion is more challenging than outdoor scenarios due to complex spatial layouts and severe occlusions, which significantly increase inference difficulty. Although transformers are effective at global context modeling, directly processing dense 3D volumes leads to prohibitive computational and memory costs. Consequently, most existing indoor methods still rely on CNNs, whose limited receptive fields struggle to capture long-range dependencies, while enlarging 3D kernels introduces cubic computational overhead. Moreover, current serialization-based methods typically adopt fixed receptive fields, lacking adaptive spatial modeling capability. To address these limitations, we propose ADA-S-Former, which serializes voxel features into structured sequences and adaptively adjusts receptive fields and coordinate representations through learnable shifts, enabling more flexible and efficient global spatial reasoning. First, we introduce the basic idea of voxel serialization and its limitations. Serialization transforms irregular or high-dimensional spatial data into a 1D token sequence and employ local grouping to reduce the computational cost of attention modeling as shown in Fig. A. As shown in Fig. B. E. Different starting points of the sequence lead to different receptive fields. Choosing the right shift is critical for serialized attention to capture meaningful spatial context. Next, we look at the framework of ADA-S-Former. ADA-S-Former adopts an architecture consisting of 2D encoding, depth estimation, 2D to 3D projection, and a 3D encoder-decoder, with the adaptive serialized transformer as its core for efficient global modeling. The core 3D encoder consists of stacked adaptive serialized transformer (ASF) blocks, which adaptively serialize 3D voxels into 1D sequences with learnable shifts, incorporate center relative positional encoding (CRP) for spatial perception, and employ convolution modulated layer normalization (CMLN) to fuse heterogeneous features. Finally, a lightweight DDR decoder outputs semantic completion results, achieving efficient global modeling with low memory consumption. Next, we show how ADA-S-Former achieves adaptive receptive fields for serialized attention. Adaptive serialized attention ASA introduces k-learnable parameters to model spatial offsets within each serialized voxel group, where each parameter corresponds to a discrete shift uniformly spaced by p/k. Using straight-through Gumbel softmax with temperature annealing, ASA dynamically adjusts receptive fields across layers. This breaks the limitations of fixed grouping and enables efficient global spatial dependency modeling with low memory cost, significantly improving scene completion quality. In indoor scenes, objects are often distributed near the scene center. Center relative positional encoding, CRP, computes the yaw and pitch angular differences between each voxel and the scene center to encode spatial information richness, helping the model focus on key structural regions and improving reasoning under occlusions in complex layouts. Our framework adopts a hybrid CNN transformer architecture for two main reasons: 1, to reduce computational cost, and 2, to leverage the global context from transformers while relying on CNNs for local neighborhood completion. However, transformers and CNNs produce significantly different feature distributions, making simple stacking harmful to training. To address this, convolution modulated layer normalization (CMLN) dynamically generates affine parameters gamma, beta from input voxel features to modulate intermediate representations, enabling effective and lightweight fusion of heterogeneous features. The total loss comprises standard cross-entropy loss and scene class affinity losses applied in both semantic and geometric spaces, promoting balanced learning of global context and local details. Quantitative comparison shows that ADA-S-Former achieves 32.5% SSCMIOU on NYUV2, surpassing the previous best method ISO, 31.25%, by 1.25 percentage points, and attains the highest or second highest IOU on key indoor objects such as chair, bed, sofa, and table, validating the effectiveness of adaptive serialized attention and center relative positional encoding. On the large-scale OCC ScanNet dataset, ADA-S-Former achieves the best overall MIOU, significantly outperforming TPV-Former, Gaussian-Former, Monoscene, ISO, and Surround OCC, with standout performance on categories including wall, chair, bed, and sofa, demonstrating superior generalization in complex, heavily occluded indoor scenes. Qualitative comparison shows that, benefiting from the ADA-S-Former, our method achieves a sufficiently large receptive field early in the network, effectively capturing global spatial structures. Compared with ISO and the baseline, ADA-S-Former produces more complete and semantically consistent 3D reconstructions, fully validating its superiority in handling complex indoor occlusions and spatial layouts. Ablation studies progressively introducing ASA, CRP, and CMLN onto the baseline show that ASA brings the most significant gain, SAIOU plus 2.68%, SSCMIOU plus 2.30%, while CRP and CMLN each further improve SAIOU by approximately 0.6%, validating the effectiveness and synergy of all modules. Compared to the baseline, directly learned vanilla shift yields limited improvement. After introducing Gumball Softmax for discrete shift learning, SSCMIOU increases by 1.35%, with the additional temperature annealing strategy, performance gains another 0.54%, achieving optimal results. This demonstrates that Gumball Softmax and temperature annealing effectively stabilize optimization and enhance adaptive shift learning. Removing CRP causes a 0.44% SSCMIOU drop, replacing projected voxel mean, PVM, with the scene physical center loses 0.39%, removing relative yaw/pitch positional encoding, RPY, loses 0.27%. This indicates that both PVM and RPY contribute significantly to capturing spatial information richness and accurately representing scene structure. In summary, ADA-S-Former combines adaptive serialized transformers with convolutional modules, leveraging key components including ASA, CRP, and CMLN, achieving state-of-the-art results on NYUV2 and OCC ScanNet with strong robustness under complex indoor layouts and severe occlusions. I welcome further discussion via email.